Yeah. Okay. Hello, everyone. So today it's my pleasure to introduce our today's speaker, Pranay Sharma, who is a research scientist in the Department of Electrical and Computer Engineering at the Carnegie Mellon University. Pranay will join IIT Bombay as an assistant professor starting January 2025. And Pranay received his PhD in ECE from Syracuse University in 2021 and finished his bachelor and master dual degree in electrical engineering from IIT Kanpur in 2013. And Pranay's current research focuses currently focuses broadly on distributed machine learning and optimization. Specifically, his research interests include federated learning, stochastic optimization, differential privacy, online learning, and reinforcement learning. So, Pranay, the stage is yours. Yeah, we can start.
Thank you, Edward, for the kind introduction, and thanks everyone for joining. So I have followed this Flow seminar for past few years, and considering the distinguished line of speakers you have had in the past, it's an honor and also a bit intimidating for me. So I'll talk about our recent work called Federated Communication Efficient Multi-Objective Optimization. This is a joint work with Barish, who is a PhD student in our group. He led this work. And also Professor Gauri Joshi, who is my postdoc advisor, and Professor Carly Jo Wong, also from CMU. And if there are any questions, feel free to unmute yourself or type them in the chat. Yeah. So let's look at certain applications where we want to talk about multi-objective optimization. First one of them is recommender systems, which are in so many applications we use nowadays. And when we talk about recommender systems, it's about recommending things, but you have to have several considerations in mind. For example, we obviously care about accuracy or the recommendations being relevant to the users, but we also care about diversity. We don't want to recommend the same kind of products to the users again and again, or we don't want very specific brands to only feature. We also care about novelty, that the user should discover new kind of content. We also care about contextual relevance. So the recommendations for someone in India would differ from recommendations for someone in Europe or in the US. So there are several trade-offs in these things. For example, perhaps the easiest to understand is the accuracy versus diversity to the user might not be very diverse, especially when the user is beginning on the platform. So how do we navigate these trade-offs? Another is a relatively recent field of personalized medicine. You get to monitor a specific individual using an array of tests and wearable devices, and then we try to make health recommendations which are personalized to the individuals. Again, there are multiple trade-offs here. We care obviously about diagnostic precision, but we also want the procedures to be cost-effective. I think there is a question in the chat. Oh yeah, sure. After the talk, yeah. We want to minimize side effects of whatever prescriptions we are making. And because this is health data, we care about privacy and data security of the patient data. Also, we want the healthcare access to be equitable across different groups, different individuals. So again, there are a number of objectives, hence some trade-offs. Perhaps the easiest to understand is precision versus cost effectiveness. Like if you do a whole lot of tests on the individual, obviously you would be very precise in your prediction, but it's not cost effective. And then there are a bunch of applications, again, in which the multiple objectives show up. For example, reinforcement learning. So this is This is an image from a paper which tried to predict short videos. It was trying to make short video recommendations using reinforcement learning. And as you can see, there are multiple, you obviously want to maximize the watch time, but there are multiple side objectives which you want to maximize as well. For example, you want to maximize the number of followers, the number of likes, the number of comments, and so on. Similarly, in computer vision, we might be interested in multiple objectives. Like a lot of work in multitask learning comes from the computer vision community. This is an example of a facial landmark detection paper, which also performed certain additional objectives to do well. And the list goes on and on, like in robotics, NLP, and more. So in this talk, we'll be talking about federated multi-objective optimization. Multi-objective optimization is of interest to me, and this seminar is about federated learning. So we'll talk about federated MOO. Here, we try to minimize a vector of losses or a vector of objectives. There are M objectives in total, and we try to learn a common model X, which minimizes all of them. We'll end up with a communication algorithm, a communication efficient algorithm, which we have proposed called CMU. And the interesting thing about this algorithm is its communication cost does not scale up with the number of objectives. This differentiates it from the existing works. We'll talk about convergence to a Pareto stationary point. So whenever we minimize general smooth functions, we can only guarantee convergence to a stationary point. In this case of multi-objective optimization, we'll discuss something called Pareto stationarity and talk about convergence to such a Pareto stationary point. We'll show that this proposed Fed-CMU algorithm has an improved sample complexity, and it achieves this under weaker assumptions than what exist in the literature. And finally, we'll also show that this algorithm achieves improved empirical performance while at the same time also reducing the communication cost. So this will be the outline of the talk. Just to ensure that we are on the same page, first I'll begin with some background on multi-objective optimization and introduce the probably the most commonly used algorithm called multiple gradient descent algorithm. Then I'll talk about the most immediate generalization of this algorithm to the federated setting called Fed-MGDA. And I'll also talk about some of its drawbacks. Then I'll introduce the algorithm which we have proposed called Fed-CMU and discuss how it improves upon Fed-MGDA. Then I'll discuss the experimental results we have, the theoretical results we have, and finally I'll conclude. Okay, so let's begin with some background. Feel free to ask me any questions. I cannot see the chat right now, so I think Edward is going to monitor it.
Yes, I'm keeping the eye on the chat, so
Thanks.
I will let you know.
Okay, so the first question is, why do we even need to do multi-objective optimization? Like, we know how to minimize scalar objectives, so why the need for this? So there are several reasons. The immediate solution when people look at a problem like this is to scalarize it, take a weighted combination, weighted sum of all the losses and minimize it. But the problem there is that it can result in multiple tasks or a small subset of tasks being severely under-optimized, right? So this is one problem. Another is that if we decide on a weighted sum of the individual objectives, how do we decide those weights in the first place? And finally, an interesting point is that scalarizing a vector of losses, like taking a weighted sum, this ends up not exploring the set of all possible solutions. So minimizing this vector of losses, this will have a set of solutions. But if you scalarize them, if you take a weighted sum and minimize that, it ends up not exploring the set of all possible solutions. And there is a very nice paper from NeurIPS last year, which showed this in certain contexts. Okay, so then let's talk about what can we do. So for that, we have to introduce a few definitions. First, we say that a solution or a point X dominates another solution X bar if the following condition is satisfied. X has to be at least as good as X bar for all the objectives. So K denotes the objectives. K goes from 1 to M. X has to be at least as good as X bar on all the objectives, but the vector of objectives should not be the same. So there is at least one objective at which X is strictly better than X bar. In that case, we say that X dominates X bar. And a solution is called Pareto optimal if there is no other solution which dominates it, right? And it can be shown that at a Pareto optimal solution, like this is fairly easy to argue, you cannot reduce one objective without also increasing some other objective, right? So if you move from a Pareto optimal solution, you will do well perhaps on one objective, but you will also do worse on some other. And if a point is not a Pareto optimal point, at any other point, you can find some direction in which you can simultaneously reduce all the objectives, right? So this is sort of a generalization of gradient descent. Once you reach some optimal solution, you cannot reduce the objective, but at any other point, there is some direction, that is the negative gradient, where you can decrease it. Okay, so next we go to stationarity or Pareto stationarity. So this is a point X bar at which a convex combination of gradient vectors is 0. So these are the individual gradients of our objectives. And there would exist some convex combination which would ensure that this convex combination is 0. And such a point is Pareto's stationary point. And this is, again, a generalization of simple stationarity we see in scalar loss functions. And if some point is Pareto optimal, then it implies it is also Pareto stationary. And from what we saw for Pareto optimal points, that if you are not at a Pareto optimal point, you can find descent directions to simultaneously reduce all the objectives. The same thing happens with Pareto stationarity, that if we are not at a Pareto stationary point, then we can find descent direction, some descent direction, following which we will simultaneously reduce all the objectives. And this is what the descent direction looks like. This is a fairly straightforward definition that we are looking for some D such that it has, so negative D's are descent direction, which would ensure that the inner product of negative D with all the gradients is going to be non-positive, right? And we say this is a descent direction. So this is essentially what we are trying to find. We are trying to find some combination of gradients, some direction, which will ensure a descent. And it turns out that this descent direction will necessarily lie in the convex hull of individual loss gradients. So this is what the convex hull looks like. You take a linear combination of the individual gradients, and the linear combination of weights will be all non-negative and sum to 1. So it's a convex combination. And our descent direction, which we defined on the previous slide, will lie in this convex hull. And MGDA is a simple algorithm which tries to find such a descent direction. And the problem it solves is the following. It tries to minimize the norm of the convex combination of the loss gradients. And this minimization happens over like a convex combinations. So this W vector lies over a probability simplex. So it has to sum to 1 and everything has to be non-negative, right? So there is a very nice paper from 2012. I think it was originally in French, which showed that MGDA, like this, solving this problem is how you achieve a descent direction. Okay. So it turns out either this problem achieves a minimum value of 0, or we will get some direction which will improve all the tasks. So if the minimum value is 0, it means we are at a Pareto stationary point. Otherwise, we will be able to find some direction which reduces the objective value for all the objectives. Okay. And just to like convince you further that I'm not making everything up, and this certainly has some advantages. So this is an example. Uh, we look at something called an multi-MNIST data set. So we are trying to construct a multi-objective problem. And how we do that is we artificially construct a data set such that every image is a combination of two MNIST digits, one in the top left corner and the other in the bottom right corner. So we get two objectives, which because we want to accurately classify both the images. And when people tried solving this two objective problem, people realized that scalarizing them or taking some linear combination did not do as well as solving a multi-objective problem. So these vertical yellow lines show what is the limit you can achieve for single objectives. And as you can see, this green dot, which is the multi-objective algorithm, achieves the intersection. So it is doing the best you can possibly hope to achieve. While all the other methods, which are either doing grid search over all possible set of linear combinations or following an equal weight strategy or something else, they are doing strictly worse. So they are not able to simultaneously achieve the best possible accuracy for both the objectives. So there is indeed some utility to doing multi-objective optimization. Okay, and just very quickly to give an intuition of what MGDA is doing, it's doing something very intuitive. It tries to find some direction which will ensure that the minimum descent across all the objectives. So you look at how much is the descent in all the individual objectives, and the direction simply tries to maximize it, right? So it tries to maximize the minimum descent across all objectives. That's all the MGDA direction does, right? Okay, so this was MGDA. Now, I think there is some question in the chat. So MGDA paper takes some loss function. If all digits are strictly on top left and bottom right, won't it introduce some bias? So I'm not sure I follow the question. So there is one digit in the top left and one digit in the bottom right. These are basically, because you have to correctly classify both of them, your loss function has two components. It's no longer a single digit classification. To ensure you classify both of them accurately, you need like some loss function on the first image and some loss function on the bottom right image. So that's why it's a two objective problem. So MGDA paper takes some same loss function like you mentioned earlier for your work. Can you clarify this question?
Hi, so you mentioned the earlier work that had loss of vectors in your work. So
Yeah.
the MGA paper takes the same loss function?
Right. Yeah.
Okay, cool.
Yeah. It tries to minimize that vector of losses rather than a single scalar loss.
Okay.
Okay, great. So now that we briefly talked about MGDA, now let's see how we generalize it to a federated setting. And then we'll talk about some of the drawbacks of that obvious generalization. Okay, so this is how federated MGDA works. At the clients, the following happens. You receive some model from the server. It's a global model. And each client initializes one model for each of its tasks, right? So you initialize the model for each task with the same global model, right? So here we have three models, three objectives at the clients, and they initialize the model for each of these objectives with whatever the server sent. Then you carry out multiple local updates. So these are computed using stochastic gradients. So LKI is the loss for task K at client I. And here we have three objectives. So we are simultaneously doing multiple updates on three models. Once we are done, we return some update to the server. So in this case, we are essentially taking an average of taking the sum of all the stochastic gradients for each task and returning it to the server. So here we were training for three objectives. So we are returning 3 updates to the server. Now let's get to the server. The server aggregates, or in this case, simply averages all the updates. So there were 3 objectives. So the server will do 3 averages, and it will end up with 3 separate vectors. And we call them delta K. K denotes the task, the objective here. And using these averaged updates, the server now solves the MGDA problem. So this is exactly what we saw MGDA does, that it tries to minimize this weighted, the norm square of this weighted sum, ensuring that the weights lie in a probability simplex, right? And once it's done, using this weight W star, the server will update the global model. It'll take a convex combination of the different updates for the different objectives and come up with a new global model. Okay. So just to summarize, this is what Fed MGDA does, right? I think there is a question. Okay.
I think I don't know. Maybe Nakib Budin. Maybe just forgot to mute. But actually, I have a question. Maybe I missed this detail. But do you consider just minimization of this? T+4. Yeah, sorry. There is somebody unmuted.
Yeah.
But okay, my question is in this setting, the goal is to minimize this. Each component in this multi-objective formulation is an average over clients, right? Each client has some local, yeah.
Okay, I get it. Right. So, okay, probably I should have put this formula, the federated formulation as well. So you have a vector of objectives, and each of these objective is average of local objectives across clients. Yeah, I have it like a few slides later, but yeah, I should have put it earlier. Yeah. Thanks for the question. Yeah.
Okay,
so we
thank you.
like we minimize a vector of objectives, and each of these objectives in itself is an average of multiple objectives across clients. Yeah. Okay, so this is the Fed MGDA algorithm on a single slide. And there are a few things interesting going on here, specifically in these 2 steps. The first thing is that the server communicated a single model, this XK, rather it should be X. So the server communicated a single model to the clients, but the clients return separate vectors for each objective. So the client is doing M times more communication, or it is doing as much communication as the number of objectives. And the second thing is that these local updates happening at the clients, these are specific to each objectives, right? So these are happening independently across objectives. And therefore, we'll see later that this will introduce some local drift across the different objectives. And this will eventually hurt the performance, right? So these are the 2 things which are slightly problematic here. And let's see how we can get rid of these. And this is precisely what our algorithm does. So finally, I'll talk about our work. So we try to improve the Fed MGDA. And let's first build some intuition for it. Suppose we knew the task weights beforehand, right? This is like just a dummy argument, but let's go on with it. So suppose we knew the task weights already. In that case, what happens at the clients simplifies significantly. So in that case, rather than training multiple models for each objective, the client can simply train a single model, this xi for the ith client, and it will take steps in the direction of this weighted sum of individual gradients, right? So earlier, this was happening. So we were maintaining a separate model for each objective. But now, because we know the weights, we can take steps in the direction of weighted sum of gradients or weighted sum of stochastic gradients. So we can now maintain a single update. And therefore, when the client returns its updates back to the server, it only needs to return a single vector, right? On the other hand, in FetMGDA, it had to return multiple vectors, one for each objective, right? So this is fine. But the problem is, how do we update the task weights? So yeah, so this helps in reducing the communication. It also reduces drift across tasks, as we'll see later in experiments. But this creates a problem for the server, because it's not that we didn't have task weights. The server has task weights, but the need for this communication arose because the server needs to update these task weights. And while updating these task weights, it needs these individual objective specific updates, these delta Ks, right? So it needs a vector for each of the objectives. That's how it gets to update. This is the MGD algorithm. This is how you update your weights, right? So now, if we are communicating only single vectors from the clients, we don't have objective specific vectors. So how do we update the weights at the server using these single vectors? Now we are not getting multiple vectors from each client. We are getting single aggregated vectors. So how do we update the weights now? This is the main challenge. Okay, so let's try to understand what happens at the server. The first line is what happens in MGDA. This is precisely the MGDA algorithm. The second line rewrites the first line with a slightly different notation. So here I have written it as a matrix vector product. And this matrix is like each column of this matrix is individual objective specific gradients, right? And rather than solving this minimization exactly, the server takes one projected gradient descent step, right? All this is straightforward. And this SM, this projection is over the probability simplex. Okay, fine. And what FedMGDA does is it approximates this vector of this matrix of gradients with these individual objective specific vectors, right? So each client sends you these M vectors, you average them across clients, and then you use these M vectors to approximate this Jacobian, and then you solve this problem, right? So that's why we need M times communication, or we need to communicate M vectors. Okay. So, but the question is, how do we approximate this matrix, which is like M cross, this is a D cross M matrix. How do we approximate it using only order decommunication? That's what we want to do. We only want to send a single vector. We don't want to send like a matrix. So this is how you do it. At each client, we have individual, like, suppose we have individual vectors which we want to send to the server. And this is going to be a tall matrix because it has M columns and each column is D-dimensional, D is very large. First, we reshape it into a square matrix. So we form a square root DM times square root DM matrix. This is a square matrix. Then we compress this square matrix using randomized SVD, and we do a rank R compression, right? So instead of like sending all root DM columns, we only want to send some R columns. And we want to ensure that R is small enough. So we want to ensure that R is smaller than this. This will ensure that the total communication cost is smaller than D. Okay. And once we send this small, like we communicate this D things or D entries or like D individual values to the server will reconstruct this root DM cross root DM matrix, right? Because we are essentially doing SVD, so we can do a low rank reconstruction of this original H1 bar, right? We had a square matrix. We do its SVD, we send it to the server, and the server will do a reconstruction of the original HI bar. And this will again be a square matrix. Now we just need to reshape it again. So it's a simple inversion of the original reshaping operation, and we get an M cross D, a D cross M matrix. So we had a D cross M matrix at the clients. First, we reshaped it to make it a square matrix. Then we did randomized SVD to reduce the amount of information we sent. We sent that information, converted it into a square matrix, and reshape it back into a D cross M matrix, right? And the communication cost we incur is now less than equal to D. And then at the server, once we have these individual matrices for each client, we can simply compute this quantity. And this was the Jacobian transpose Jacobian we needed to update the weights. Okay. Yeah.
Can I ask some quick question?
Yeah.
How do you reshape that? Is it important how you reshape into square matrix, or you can do it arbitrary? But what was the rule?
Yeah. Yeah, so we were not super concerned about the reshaping. All we did was we took a tall matrix and we stacked entries such that it became a square matrix. And like, I think Barish tried a few approaches and it didn't have a lot of impact.
And in the end, the goal is like to communicate this HI bar or HI tilde using
Right,
all of the communications, right?
right,
And then you okay, I see.
right, right.
Yeah.
So we want to communicate this huge D cross M matrix, but we only want to do it using order D communication. So first we make it a square matrix. We compress it using randomized SVD such that like we control the rank of this matrix so that our communication is constrained. We send it, we construct this square matrix again, and then we reshape it again to the stall matrix, which is HI, and then we can compute this thing. Right?
Thank you.
Yeah.
Hi, Pranay. I have just one quick question here.
Yeah.
On this same slide, 21. So, in terms of reducing the communication cost, it seems very promising. But I'm also a little worried about the loss of information. So when we transpose or rather convert this by reshaping and then applying the singular value decomposition, what are the chances, or do we calculate in any way how much information we are losing? Because in some of the application, please go ahead.
Yeah, so you have preempted my next slide. So like, let's go to the next slide and find out.
Oh, okay, sure.
Yeah. Okay.
Thanks.
So like this is sort of a notation I use later in the talk. So I denote like some operation we are doing on the original tall matrix called Q. And in our case, it will be first we reshape it, then we compress it, and then we reshape it back to a tall matrix, right? And the compression I just talked about on the previous slide was randomized SVD. As the question by Amardeep, we also experimented with a few other compressors. So let's look at what happens. So we tried with 3 compressors. One was randomized SVD, one was random masking, and one was top case sparsification. And to find out like how do they perform, we compared the relative error you get. And this relative error is computed relative to sending the full tall matrix, right? So we sent the full tall matrix, and then we compared how much error we incur by compressing, right? And as you can see, so we tried 2 different approaches. Like I won't go into the details of this two-way communication thing. This was basically error feedback. But these red rectangles show the error in percentage, which you get with randomized SVD. So we experimented with a bunch of data sets. These are the mean values. And as you can see, this is doing better than like things like top case sparsification, in which you send the largest entries of that square matrix, or random masking, in which you send like randomly chosen entries of that square matrix. So does that answer your question, Amardeep?
Yeah, I think this is something. It will give me a comparative analysis.
Yeah. Okay.
Sparsification I have used before, but the randomized SVD I haven't used before. So would you recommend this one for I mean, is there any limitation on the kind of task that we can choose, or is it like more generalized? Or
So there are two things to consider here. First, like we did that conversion from a tall matrix to a square matrix so that like we could control the communication cost. If you try to do SVD with the tall matrix itself, you cannot do better than D, right? So that's why conversion to square matrix is necessary. Another reason is that this SVD would also incur some computational cost, right? So if you make it a square matrix with small dimensions, you can control that computation. I think one thing to keep in mind is that like this computation which randomized SVD incurs, this should not like exceed whatever power budget you have, right? So in our case, we realized that this is not a significant cost. So that's why we went with randomized SVD. But in some applications, like if your D is extremely large, in that case, probably it won't be like you will need to go with something which is much cheaper. Like random masking is much cheaper because like it's just taking a few entries from the matrix, while randomized SVD, this is some computation, right?
Yeah. I think that's a very pertinent point here, that the application must be kept in mind, and then we can compare the different compression methods. Yeah. Thank you so much for that.
Yeah. Thanks. Okay, so coming back to the problem of weight updating.
Sorry, Pranay, for interruption, but there is a question in the chat.
Let me look at it.
Yeah, I can read.
Are you trying to eliminate small weight updates? So we are trying to make sure that from that square matrix, if there is low rank structure or if there are some dominant components, we only send those dominant components. Like the point of SVD is to find out like some principal components or whatever the dominant subspace, to identify the dominant subspace in your entire full dimensional space, right? So that's what we are trying to achieve. That introduces some error, as you can see in this table, but it helps us save on communication. Does that answer your question? Okay, thanks.
Yeah, yes.
Okay, so coming back to what we wanted to do, we wanted to update the weights at the server. That's why we were doing all this detour, and we wanted to do it in a communication efficient manner. So this was the problem we wanted to solve, and what we just discussed allows us to approximate this with this thing called G. And G essentially is computed using only order decommunication. And once you have G, then you can update the weights at the server, right? So we took care of the excessive communication which FedMGDA had to do. So now let's introduce the algorithm FedCMU. It's quite simple. For like ease of understanding, I've colored whatever happens at the server with blue and whatever happens at the client with this green looking color. I'm not very good at identifying colors. So first, the server selects a subset of clients. We are considering partial participation. So the server selects a subset of clients, sends its current model X to all these clients. The clients will compute like some approximation of this Jacobian matrix, and then it will send it using the compression scheme we just discussed. So it's not going to send D cross M matrix. It will send only D-dimensional entries. Then at the server, starting from this small matrix, you construct the original tall matrix and we compute this G matrix, right? This G is simply used to update the weights, and this is what happens next at the server. And these weights are then sent to the clients, okay? With these weights, the clients carry out multiple local updates. So now they are doing this, they are taking gradients using weighted sum of individual gradients of all objectives. Once the clients are done, they compute the update, basically how much they differ, like how much distance they have come from the original model sent by the server. They send these updates back to the client, back to the server. And the server averages these updates to update the global model. Okay, so this is what FedCMU looks like. And the communication cost, In Fed MGDA, so this S here stands for stochastic. So Fed MGDA or Fed SGDA, they are both the same things. The only difference is stochastic gradients or full gradients. There, the server communication cost was D. In our case, the server communication cost is D plus M because the server also sends this weight vector to the clients. And because M is typically much smaller than D, so there's not much difference. But in the client communication cost, the communication cost for each client, there's significant difference. Fed MGDA needed M times D, while Fed CMU requires only 2 times D. So the first D communication is happening here, and the second is happening here. Okay. So this is the algorithm. Next, I want to talk about the theory. And first, I want to highlight the limitations in the theory of Fed MGDA. So this was the problem they were trying to solve. You have M objectives. Each objective is an average of individual local objectives of different clients. So here I denotes the clients and this K denotes the objectives. M is the number of objectives. N is the total number of clients, right? So these were the assumptions which the Fed MGDA analysis takes. And the interesting thing here is the second assumption, where they say that you compute your stochastic gradient, any stochastic gradient, at 2 different points using 2 different samples, right? And their difference is going to be bounded by this quantity. So this is not a big deal. This can easily follow from just assuming bounded variance and smoothness assumption. But how they use it is interesting. So somewhere in the paper, they say that like this can be satisfied by sufficiently large constants, right? But eventually in their analysis, what they end up is the following. So eta is the learning rate, and they have this one last term at the end, which depends on this alpha 2 sigma square, this alpha 2 sigma square. And then to ensure convergence, they choose this alpha 2 to be of the order of the learning rate. But the problem is, like, I mean, this is not fair. The kind of assumption you are implicitly assuming that this constant would be of the order of the learning rate. And I can choose my learning rate arbitrarily small, which means my assumption, the right-hand side of my assumption can go arbitrarily small, right? If you think about it, like if you try using just bounded variance and smoothness to derive this condition, this alpha 2 turns out to be a constant. It's not of the order of learning rate. It's some scalar value, right? So this is, yeah.
Yeah, maybe a comment here. So perhaps it can be controlled by mini batching, but of course it will increase the like Oracle calls, number of Oracle calls per client.
Right.
Yeah.
Right. Yeah.
So we can make
you
alpha
can
2
increase
with
mini
mini
batch,
batching.
but then it leads to worse complexity. So this is a slightly strange assumption. I think they needed it for their analysis, but I wanted to highlight it and we'll get rid of it. Another thing to note here is that they have this M square sitting here, right? And therefore their complexity scales with M to the 4. Like you can figure it, you can argue it that their complexity will grow with to the 4th power of the number of objectives, right? This is really bad. Like if I can understand complexity which is linear in the number of objectives because I need to solve each objective, but why should it be to the power of 4? So these are the 2 limitations I think of this Fed MGDA paper, and let's try to get rid of them. So this is the problem we are trying to solve. First, let's look at the assumptions we make. And these are pretty standard, like smoothness, unbiased stochastic gradients, bounded variance. Bounded gradients, this is one strong assumption which we make, and like we are still trying to figure out how to get rid of it. I can talk more about this if someone is interested. And another strong assumption we make is of unbiased compression with bounded variance. This is fine, but this is a strong assumption. A randomized sparsification would satisfy this, but a top case sparsification won't satisfy this. And the randomized SVD which we use also doesn't satisfy it. So this is just for the sake of theory. It like our algorithm with randomized SVD does not satisfy this assumption. Okay.
Quick follow-up question I wanted to ask as well. But will this randomized SVD satisfy this contraction property without unbiasedness? I mean, there is a class of not necessarily unbiased, but contractive compressors when actually you have similar property as the second one, but Q should be smaller than 1.
I think it does, but I'll have to check it again. I think what you are saying, it makes sense, but I think I'll have to check this again.
Because everywhere, like in numerical experiments, in the tables that you shown, this number was always in percentage. It was smaller than 100, meaning that this quantity Q was, and it was actually much smaller than 1. This quantity Q. So it's a good thing.
Right.
For compression operators, for contractive compression operators.
Right. Okay. So with these assumptions, this is what the convergence looks like. So let me explain this expression a bit slowly. So we are trying to minimize weighted sum of the gradient. So this is what MGDA was trying to do. This is what we are trying to do. We are trying to minimize it over the number of rounds. So here T is the number of rounds. These are the notations you see on this slide. Let me explain them slowly. So T is the number of rounds. We are trying to minimize the norm of the weighted sum of gradients over communication rounds. And this error can be decomposed into 4 sources of error. The first is the error which you could incur if you were solving the same problem for a scalar loss in a centralized setting, right? So instead of this vector, if you had minimize f of x and you are solving it in a centralized setting, then you would definitely have this. Then the second source of error comes from partial participation because we are only selecting a few clients in every round. So we get this source of error. The third comes from local drift because clients are carrying out multiple local steps, namely tau local steps. Oops. So this is the third source of error. And the final source of error comes from minimizing a vector of losses. So because we have multiple objectives, so this is the final loss which we see, right? So maybe let me specialize it to a few settings for it to make more sense. And before that, with appropriate choices of these parameters, we can show that this is the convergence rate you can get. Here, T is the number of rounds. I'll come back to this in a few slides, but let's look at a few special cases first. So suppose we fix our scalar weights, like our beta, the step size with which the server updates these objective weights. If this was 0, in that case, we are simply minimizing a scalar loss. We have taken a linear combination of individual objectives and we are minimizing that, right? In that case, it turns out you can significantly simplify this bound. And the bound we are left with is exactly the bound which we get with Fed average. Right, so this exactly reduces to Fed average. Like you will completely get rid of this, and these terms would also improve slightly. Right, and there is reason for that improvement I can get into if there is some interest, but this exactly reduces to Fed average. And let's look at the dependence on the number of objectives. So again, this is the problem. And if we try to achieve this gradient norm square smaller than epsilon, then this paper is a centralized algorithm and it achieves quadratic dependence on M, right? The dependence on epsilon is fine. You cannot do better than 1 over epsilon square, but the dependence on number of objectives is quadratic. Fed MGDA achieves like to the 4 in the number of objectives. On the other hand, we are able to achieve linear dependence on the number of objectives, right? And you can, like, this is the best you can do, right? Now, let me point out some limitations of our analysis. So I mentioned that with appropriate choices of parameters, this is the bound we get. But there are a few things missing here. First, we have to make the strong assumption that the gradients are bounded, right? And second, we do not get any linear speedup with the number of participating clients in every round. If there was an N along with T, that would have been good. That is desirable, but we do not achieve it. And that results from this bounded gradient assumption. Also, we do not achieve speedup with the number of local updates tau. This is again a result of the bounded gradients. And it turns out the culprit here is the inner product terms. So very briefly, if you recall the smoothness quadratic upper bound you get from smoothness, there is an inner product there, which contains the gradient and the difference of two iterates. That inner product is much easier to handle when you have simple minimization problem with a single objective. But when you have a multi-objective problem, that inner product term creates a lot of trouble. And we are still trying to figure out if that inner product term can be controlled and if we can get rid of this bounded gradient assumption. If we do that, in that case, we'll achieve linear speed up in N. We'll also get speed up with number of local updates. So that's the main limitation of our analysis. Okay, now let's very quickly look at some experimental results. I have about 5 minutes. So we created or looked at a bunch of data sets. So first set of data sets was similar in spirit to what I showed on one slide earlier, that you have some kind of image on the top left and some other kind on the bottom right. So we created multiple combinations, MNIST plus fashion MNIST, multi-MNIST, which I showed earlier, or CFAR10 and MNIST. So these are images from MNIST plus fashion MNIST. So we randomly sampled images, one from 2 data sets, and we created a new image. So there are 2 objectives. And another was a celeb A data set. This is a famous data set. Every image consists of 40 attributes. These attributes are if the person is wearing glasses or not, if they have bangs or not, if they have wavy hair or not, and so on. So you get 40 binary classification problems for each image. And therefore, we end up with 40 objectives, right? So this is to show how the methods does when you have a lot of objectives. Okay, so first, let's look at the mean test accuracy for 2 data sets. In all the experiments, we had 100 clients in total, and in each round, we selected 10 of them. And here I've plotted the test accuracy averaged over all the objectives. So in the left figure, there are 2 objectives. So it's averaged over 2 objectives. In the right figure, celeb A, there are 40 objectives. So this is an average over 40 objectives. And the thing to note here is that compared to Fed MGDA, we are doing significantly better. So Fed CMU is the algorithm I just described. Fed CMU Pref is another algorithm where you get to specify preferences, like which data set, which objectives you prefer to minimize more than the others, right? And in both cases, we do significantly more. And part of the reason is that the Fed MGDA, which I described earlier, because for each objective, you are doing local updates at the clients in parallel. So they tend to drift apart. And this drift hurts you in performance. And we actually looked at how this drift looks like and what are the effects of this drift. So it turns out that as we increase the number of local iterations, tau, Fed MGDA, it tends to have worse performance, while the performance of our method, Fed CMU, tends more or less stable. Right?
Sorry, Pranay, I have just one question. Can we go back to the slide number 35, the earlier slide? Yeah, so here you mentioned about the taking average of the objectives. So here, how do we consider the Pareto optimality between these objectives?
So in a few slides, I'll have another figure in which we have plotted how we do on all the objectives. But here we minimize all of them. And whatever test accuracy we get on each objective, we simply average them plot here. I think perhaps your question would be answered on that slide. It's, I think, in 2 or 3 slides. So let me get to that.
Sure.
Yeah, so here, as I was saying, as we increase the number of local iterations, because FedMGDA has that large drift, so the models for each objective drift apart, and this really hurts performance. But in our case, because we are only training a single model even at the clients, so the performance is more or less stable as we increase the number of local updates. And this is the slide I was talking about. So here for the Celeb A dataset, there are 40 objectives, and we have plotted how we do on all of them. And as you can see, these are the loss values. So the closer you are to the center, the better you are doing. So Fed MGDA is the green line, and black one is Fed CMU Pref, and purple one is Fed CMU. So as you can see, the purple one, almost for, I think for all the tasks, you are closest to the center, right? So we are consistently doing better across all the losses or all the objectives. The question about Pareto optimality, as I said, when you have non-convexity, you cannot really ensure Pareto optimality. You can only hope for Pareto stationarity. So that's why it's very difficult to quantify how we are doing on the Pareto front. So we can compare the average accuracy or the individual accuracy or the individual test losses, which we do here. And yeah, if you have some thoughts on how better to portray the performance or compare the performance, yeah, this would be interesting. Okay. And this Celeb A5 is another data set we constructed out of Celeb A. I don't know if Barish constructed it or if it exists in public domain also, but this is out of those 40 attributes, we create 5 groups of 8 attributes each, and then we compare performance on those 5 objectives. Again, we are doing better. Okay, so in the interest of time, I'll skip the preference part. Very briefly, we also enforced preferences across objectives. So if you have 2 objectives, we enforce how much you prefer one over the other. So for example, this shows that we prefer the first 4 times as much as the second. So you should do 4 times better, or you should minimize the first loss 4 times more. And this is the performance we achieve for different specified preferences. This gray region is the absolute best you can do. So these dashed lines are the minimum loss values you can achieve on these individual objectives. So this gray region is basically off limits. And we are able to very closely touch this gray region for different preferences. And another thing that these preferences are more difficult to satisfy as you go to significantly more different weights. So as you go to the right bottom or the top left corner, these become difficult to satisfy. Around here, these are like you can satisfy them very accurately. So I have some open questions I can get into, like if there is interest. Basically, there is a lot of intersection between multi-objective optimization and multitask learning, but the understanding is very incomplete right now. The most pertinent to me is that all the standard optimization metrics like sharpness or minimum loss, they don't really explain the generalization gap between single task and multitask learning. So there is a lot of work to be done here. And just to summarize, this was the problem we were considering. We want to minimize M objectives simultaneously. Each objective loss is an average over the client losses. There are N clients. We proposed a communication efficient algorithm called FedCMU. Its communication cost, unlike the existing algorithms, its communication cost does not scale with the number of objectives M. Then we showed convergence to Pareto's stationary point, and our complexity is linear in M compared to the existing methods where it was quadratic or to the 4th power. And we achieve this under weaker assumptions. We get improved empirical performance. And we also have some work on preference-based multi-objective optimization, where you get to specify which objectives you want to minimize more than the others. This is the link to the paper. Thank you so much for your attention. I think there is some question in the chat. Is there any code base available? So Paresh is the one who does the experiments. I am sure he'll release it sometime soon. Yeah.
Yeah, thank
Pranay.
you.
Edward, do we have like a couple of minutes more, or if not, I
Yeah,
can.
just yeah, we have. I just wanted to thank Pranay for an excellent talk, and yeah, we have time for some questions. I think if Pranay also has time.
Yeah, I do. I'll also type my email address in the chat. If there are any follow-up questions, feel free to reach out to me.
Yeah, maybe we can use extra 5 minutes, and then it will
Yeah,
be
so
fine.
I just
I
typed my
hope.
email address in the chat.
Thanks. I have just one question that I was wondering about while looking at the experimental results. So, in terms of communication, we did, applied some novel methods here. But in terms of accuracy, did we do anything with the federated, learning method itself? Like, what do you think accounts for improvement in accuracy?
Yeah, so let me go to the one of the experiment results slides. Yeah, so one thing which helps in this case is definitely that we reduce the drift which happens across models. So in Fed MGDA, because the clients are essentially starting from the same global model, but for each objective, they end up training different models, right? So these models drift apart, and then at the server, you are averaging them again. Instead,
Right.
we keep a weighted combination of the individual objective gradients, and we move in that direction. So this helps reducing drift, as I show here, and this explains the performance difference as well, which we see. And the interesting thing here is that this drift gets even worse as you increase the number of objectives. So the differences in performance is significantly more for Celebi, where you have many more objectives, so you will have more drift. It is also worse if the two objectives you have. For example, we also experimented with MNIST plus CFAR10, right? So these two data sets are very different from each other in terms of how difficult they are. In that case, also this difference amplifies. So if there are too many objectives, or if the objectives are significantly different from each other, this drift really hurts performance. And therefore, we are able to, by maintaining a single model and working with the weighted sum of gradients, we are able to eliminate that drift to a large extent.
Yeah. Yeah, thank you for explaining. I was also thinking that as we increase the number of objectives, then actually we can find out the difference, the real difference between uh, updating the weight together or in a separate way. I was a bit surprised that in the first case,
Well,
the
so
MGDA. Yeah.
yeah.
No,
Yeah, go ahead.
I was just trying to complete that the MGDA, although they are talking about the multi-objective optimization, but when they transfer between the client and the server, they transfer separately for each objectives.
Right. And like the reason for that is, so as we discussed, like it's sort of what you would do intuitively as the first step. So let me go back to that slide. So the reason is that to solve this problem, you kind of need the gradients for all the objectives, right? So therefore, like they end up sending these separate updates for each objective, and then they average them at the server and compute the weight updates. Like we had to do something extra in order to uh, like eliminating this need for communicating these matrices, these D cross M matrices, and communicating like just D values. So like intuitively, it makes sense. It was like the first logical step.
Yeah.
Yeah, but like there were a lot of things which happened in the background, which like in trying to communicate the matrix, you had to train multiple models, and that introduced drift and so on. Saksham has a question. Go ahead, please.
So, like, your work does touch upon the bit width part of federated learning, like lower
The
bit width
which
and
the
bit
which
width,
part?
bit widths. So lower bit width, so 8-bit or
Oh, okay.
yes.
Uh, Not really, but like these compression schemes, you can compose them together and like get some additional compression while losing some performance. So I think adding further quantization on top of our compression, like this would be, I think, relatively easy to do.
Okay, so that would work in a different setting.
No, like you can do this in our setting also. Like we did not explore it, but what I'm saying is these compression schemes are often quite composable. Like for
Yeah,
example, if you are doing sparsification, you can do quantization on top of that.
I
So
see.
in our
Yeah.
case also, like while communicating those D values from each client, you can quantize them.
Okay, so but would there be any trade-off?
There would be loss in performance, definitely. But like we did not explore how much you can compress without observing significant loss in performance. Uh, I suppose you would be able to compress a bit without losing much performance. Like, for example, you will be able to compress from like 32 bits to 8 bits or so. Beyond that, there would definitely be loss in performance.
Okay, I see. And as of now, there is no code base available for this work.
Not yet because the paper is still under submission, but as soon as it gets accepted, I think we'll release the code base soon. Like we have released code bases for most of our papers in the past, so we'll do that for this also.
Okay, good.
Okay, I also got a question by SK Cash3. The question is, I'm interested in continual learning under a full setup where clients can simultaneously observe different tasks. Can we use this method to convert a continual FL as a multi-objective problem?
Uh,
So, yeah.
so to be honest, I don't have a lot of understanding of continual learning other than like it's adjacent to multitask learning. Uh, like I suppose it should work. I have seen a few papers on continual learning in the federated setting, but yeah, I don't have any insightful answers for this. Sorry.
Yeah, it's fine. Thank you. Also, yeah, if anybody has questions, I think we have time for maybe one more. Yeah, but anyway, there are many questions during the talk, and thank you, Pranay, for handling them. Perhaps maybe one short question, like about this algorithm. You say like it's sufficient to do one step of projected gradient descent. Did you try at least numerically to this? Yeah, for computing the weights. Did you try numerically to do multiple steps and how the method behaves when you do more than one step?
Uh, I like Barish is the right person to answer this question if he experimented with multiple steps or not. But I think this question is interesting for a different reason. Uh, a strange phenomena which happens in this multitask learning or multi-objective optimization is that these weights, like their effect on the eventual performance is not very well understood. Like people have realized that in a certain settings, even if you keep this weight fixed, even then you can achieve better performance than when you are updating these weights. Like the intuition was that, and in the most general case, when you are updating the weights, you are solving a more general problem, so you will potentially reach a better solution. But in practice, it is not always the case. So this is again an interesting open question that when does updating these weights help and when it does not? Like there are papers going both ways. Like I remember there was a paper in Europe 2022 which showed that like you just need to keep the weights fixed and still you can get the same performance as other methods which vary the weights or even outperform them. But there are papers which argue other way also. So this is I'm not sure if I answer your question. Like in our experiments, I'm not sure if we experimented with it, but like the more general point is that this is not well understood what is the effect on eventual accuracy.
Oh, yeah. Thank you for the answer. And also there is a question in the chat: is the drift due to asynchronous updates?
So I think the question is about the drift which Fed MGDA gets. That is not really happening due to asynchronous updates. The drift is happening because, let me go back to, yeah. So the drift is happening because, so actually this should be X, this should not be XK. The server sent a single model to all the clients, and then the clients initialized uh, the model for each objective with the same model. So this XK is actually X. But then the clients started training multiple models for one for each objective, right? That is why the drift happens, because you started from the same point, but then you are training multiple models and each of them is trying to minimize a single objective. So that is the reason of drift. It's similar to what drift is in federated learning, that you start from the same model which the server has sent you, but then because every client is minimizing their own local losses, so they tend to drift apart.
Yeah, but here maybe there are two kind of drifts. One is due to this difference between tasks, and another one, the difference between data.
Right. Yeah, so there is objectives as well as there is drift due to clients, and then there is also drift at the same client between two models for the two objectives.
Yeah, I think, thank you once again for very interesting talk and for the discussion. And I think it's already we are
Thanks,
already
everyone.
a bit late. Thank you. So I'm stop recording and